Hello everyone. So today I'll be talking about how I'll be implementing AES-128 encryption algorithm using hardware software implementation on a DE1 SoC. So myself Samarth Nandish and I have my teammate Ravi. So yeah, let's continue. So as we start with introduction, so what we're doing is we are trying to implement AES-128 encryption algorithm on our hardware and hardware and software co-implementation. This is because the software itself can do both the encryption and decryption, but it's just that the FPGA in itself is an accelerator, hardware accelerator. So what it does is it basically enhances the encryption speed. So yeah, it basically encrypts it faster. So that's why we are trying to implement AES-128 on both the FPGA and our HPS. So how would we go about on implementing this? So as we talk about FPGA implementation, so it'll consist of 12 cycles of AES-128 encryption steps. So which includes modules like substituting bytes, shifting rows, mixing columns, and adding route keys. So this is the core four functionalities of AES-128 to produce the ciphertext. Now this basically, FPGA will produce 128 bits of ciphertext that is sent back to our HPS. Now, what happens in the HPS end is we have our modified ARM processor. So, what it does is it will basically read the ciphertext and then it has to decrypt it. So, basically, the whole process starts off with our HPS, taking up the plain text, 128 bits of plain text or 16 ASCII characters here in our case, and then it generates a key by itself, and this HPS basically sends this plain text and key through our AXI light bus communication that is there on our board to our FPGA, which basically does the encryption and uh, sends it back to our HPS for decryption. So yeah, this is the overall view of what needs to be done. So yeah, here we can see the interface of components. I've simplified and showed it in a diagram. So our ARM HPS basically starts off with generating a random key, and then it takes 128 bit of plain text from the user. And yeah, now these two will be communicated to the FPGA. Now, FPGA in itself can't communicate with the HPS because HPS is basically it looks everything as a memory, and FPGA if it needs to access it. So what we have done is we are actually mapping the PIOs or the ports on whatever the components we have as memory on our HPS. So that's how basically we communicate. So that's why what it's doing is our HPS communicates to FPGA through our PIOs, which I'm shown in the diagram here. So as you can see, it sends the random key, and that since our PIO registers are 32-bit size, we'll have to, cut it down and send it as 32 bits for 32 bits each. So yeah, that's what is being sent here. It's dividing the data of 128 bits into 4 of 32 bits. So same is done for plain text, and this is sent. And as I said, it must take and encrypt it. And after encrypting it, the FPGA sends those 128 bits and again divides it and sends it back to our ARM HPS, which will basically decrypt it. So the rounds of execution, as I said, it has core functionality. It has four core functionalities. So based on that, we have 12 steps or 12 rounds. So the first round will basically be XORing the plain text with the key, and then we have the cycles 1 to 10, which will basically do the encryption process where we have defined a substitution table for substitution bytes where our data will be taken and substituted with one in the lookup table, and then it shifts the rows as it says the name, and then it makes up the columns, and it does the same thing over and over again for it does that for 10 cycles, and then at the 11th cycle it basically finishes it and sends back the ciphertext. Now let's continue to see what we have done here. So here is our Quartus project. As I said, this is our lookup table where we switch up the data that we have with the reference in this box, and then the core functionalities, yeah, the core functionality here. And this GHRD top module is basically the golden, you know, golden. It's like a black box for HPS FPGA communication, which basically has all the ports that you'd ever need to communicate on the FPGA. So yeah, it has all the ports, and now I've generated the extra whatever the ports that I want to communicate with HPS, basically exposing those ports to HPS. And yeah, as you can see here, I've basically mapped whatever I want, the key, the plane, and the ciphertext, and this control is basically uh, that is sent by the HPS to, when it's like a start signal, when it sends one, then the encryption process starts. So that is what is going on. And then, as I said, the 32 bits again have to be combined to make the 128 bits. So that is what is going here. And here is our module that is being, called into our top module for accessing. So yeah, having done this, I've already compiled the program, and as you can see, it uses 5,894 ALMs and 9,121 ALUTs and some 8 partial LABs. And yeah, it uses boot from FPGA and clock and the other components, as you can see. So it is a computationally heavy program. So yeah, that is what we see on the FPGA. And basically, again, if I had to show the timing here, so the Fmax is found to be 86.74. So yeah, this is our Fmax. And let's move back to the slides. As I explained, this is the memory mapping where I've mapped the PIOs that I need to communicate with HLS uh, through this address mapping, and then the summary of whatever the uh, components or the resources used, and then I have the timing here. Now, yeah, so check how or if the FPGA really works. Let me just go ahead and so I have ran a simulation here, online simulation. So as you can see, I've given various test cases here. Like I have 10 test cases, and I've run the simulation to see if the encryption actually works. So as you can see, with every case, it takes 11 cycles, as I explained, and the results came out to be as what we expected. So having done that, as you can see, it's pretty much looks good. Let me just go ahead. Yeah. So this is what I showed that about the encryption end of the FPGA. Now coming back to HPS, as I said, HPS should basically generate the key, take the input from the user, and then send it back to FPGA for encryption because it's an accelerator, and get that back and decrypt it. So yeah, here is a test case where I've just, tried to check if our HPS is receiving the, cipher data from the FPGA. So here are a few cases that I ran and to verify that the bus communication is actually happening correctly. And then, so I'll be showing how I implement this program. Everyone, so now I'll be showing the implementation of the same. I've already mounted my hard drive here. So let me just go ahead. I've also programmed the FPGA at the same time. So let me just go ahead and run the program. As you can see, the bridge has been initialized here, and the random key, 128-bit encryption key, has been generated by the HPS. Now it's just about, as I said, it asks about 16 ASCII characters from the user itself. So if I were to type random, okay, let's go ahead and, as you can see, it's been implemented successfully. Now let's go back here. Now the ASCII has been converted to hex here, as you can see, and then, as I said, those 128 bits has been divided, and as you can see, it's been sent here through the, this is how it's been sent through the AXI bus, so that it is compatible with the PIOs on the FPGA because they are 32 bits. So yeah, as you can see, it's arranged here,
and then the data, as you can see, is being transmitted via axial bus, that is are present between the HPS and the FPGA. Now the encryption has been triggered, and using this we got the ciphertext that we got here. This we got from the FPGA. Now the once we get that, then it must be decrypted. So when I say hardware decrypted here, it means about the decrypted software decrypted by the hardware. And since I've also used software encryption and software decryption, as you can see there is software encryption and the software does the decryption here also. As you can see, both are matched, and we have a complete result summary here showing how the encryption key, what the encryption key is, the hex data, and the data is sent here, and as you can see the hardware data here and the software data, relevant data, and yeah, as you can see all the tests have been met. Thank you.